All right, hello everyone here. I have some slides to cover, Standard 3 in calculus. We'll go ahead and get started. Standard 3 focuses on defining what a limit is equal to using a variety of different methods, tabular, graphical, and algebraic. What is a limit? What is the notation for a limit? And how can we evaluate a limit using a variety of different methods? By making a table, looking at a graph, or using some algebraic properties. So first off, here's just kind of an informal definition of a limit. Let's look at the notation below. Limit is LIM. So the limit as x approaches c, this x arrow c is read out loud as x approaches c. So the limit as x approaches c of our function f of x is equal to a value called L. So what this means is if f of x becomes closer and closer to L as x approaches c from either the left or the right, from both of the two sides, as I get closer to c from values less than c, as I get closer to c from values greater than c, if the function approaches L, if it gets closer and closer and closer to that value L as x approaches c, then the limit of f of x as x approaches c is now going to be equal to L. Something to keep in mind is a limit defines what a function tends to be equal to. What is the tendency of our function, of our graph, as x gets arbitrarily, infinitely closer to c from both the left and the right? So what we're looking at in these next couple of slides is how to find a limit of a function using a variety of different methods. By looking at a graph as we see here, by making a table, or using some algebraic properties. So what we have in this picture is a piecewise function. Several different points are open, where the function is undefined. Several different points are closed, where the function is defined. So let's find some values of the function and the limits of this function for different x values by looking at our graph. So some good review here. What is f of 1? What is the value of the function for when x equals 1? Well, I can choose either 1 or 2. And since the circle's closed at the 2, that indicates the value of the function for when x equals 1 is defined to be 2. Now let's investigate what the limit as x approaches 1 of f of x is equal to. So this isn't what the function is defined to be. It's what the tendency or behavior of the function is as I get closer and closer and closer to our value of 1. So as I approach 1 from the left, the function is getting closer and closer and closer to 1 on the y-axis. The function takes on values closer to 1 as I get closer and closer to 1 from the left. Now the function, as I get values that are greater than 1 from the right, for values that are greater than 1, as I get closer and closer to 1, the function approaches the same value of 1 on the x-axis. So this indicates that the limit as x approaches 1 of f of x is equal to 1. Notice that what the function is defined to be equal to and what the limit is equal to for x equals 1 can be different things. That's not a problem. Now let's look at a different example, a different value. What is the value of f of 2? Well, using the same process as before, the value of f of 2 is equal to 2 for this point right here. Now, what is the limit of our function as x approaches 2? So we're going to see what the function tends to be equal to from the left and the right. So as x gets closer to 2 from the left, the function gets closer and closer to 2. As I approach 2, the function gets closer and closer to 2 from the left. Now from the right, as I get closer and closer to 2, the function tends to be closer and closer to 3. The closer I get to 2, the closer my function is equal to 3. So because I approach a different number from the left than I would from the right, this actually does not exist. Limits can either exist, as we saw in the previous example, for when x gets closer and closer to 1, or they may not exist. If a function doesn't approach the same number from the left as it does the right, that's one of the couple different reasons why a limit may not exist, and we'll investigate those further here in this minute. Let's look at one more. What would f of 4 be? Well, f of 4 actually does not exist. There is no defined point for our function when x equals 4. Let's see what the limit as x approaches 4 of f of x would be equal to. As I get closer and closer to 4 from the left, I get equal to 2. As I get closer and closer to 4 from the right, the function, it gets closer and closer to 2. So this limit of f of x as x gets closer and closer to 4 is equal to 2. Once again, notice that these are different things. These are different things. I'm not describing what the function is defined to be. I'm describing what the function tends to be for values that get closer and closer to 4. Were the function to be defined, it would make a lot of sense for it to be equal to 2, but in this case, it's not defined. So this kind of depends on what your graph would be. Okay. We saw a second ago why a limit might fail to exist. There's actually 3 different reasons, and I've got an example of each of these in the pictures down below. The first reason we've already seen. The limit of a function would fail to exist if the behavior of that function differs from the left and the right sides. So the behavior differs. And that happens at x equals 2, like we saw right there. For values that are less than 2, the function approaches 2. From the values that are greater than 2, the function approaches 3. I'm approaching 2 from one direction, I'm approaching 3 from another. So the limit as x approaches 2 of f of x does not exist. A second reason that a limit would fail to exist would be when the function is unbounded. As you can see in the middle picture, as x gets closer and closer to 1, the function increases without bound. As x gets closer and closer to 1 from the right, the function gets higher and higher and higher. As x gets closer and closer to 1 from the other side, x gets higher and higher and higher. Every number that I get that's closer to 1, the function will increase without bound. That happens when our function has a vertical asymptote. In this case, there's a vertical asymptote at x equals 1, which means that as I get closer and closer to 1 from any direction, the function has unbounded behavior. It increases without bound. Okay. The last example is one that doesn't happen too often, but you will see it every now and then. It's when a function has oscillating behavior. Oscillating refers to the fact that it's bouncing back and forth between 2 different values. Sometimes it's equal to this, sometimes it's equal to that. I'm approaching one value, then I'm approaching a different value. Then I'm approaching the same value, then I'm approaching the other value. Then I'm approaching one value, then I'm approaching the other value, and so on and so on and so on. An example of that would be sine of 1 over x. As x gets closer and closer to 0 from the left and from the right, the function bounces back and forth between either 1 or -1. Sometimes it's approaching 1, sometimes it's approaching -1. Because it's not approaching the same number from the left and the right, the limit doesn't exist because of oscillating behavior. We'll see an example of that here in a second. I think I actually look at sine of 1 over x. So as we saw in our outline of the standard, there are three ways to find a limit. Numerical approach by making a table of values. The graphical approach, which we've already kind of seen, how we can look at the graph or a picture and investigate what a limit of a function would be. And then an analytic approach, where we use algebra or any kind of simplification techniques to define a limit. Let's investigate some limits using a variety of these approaches. So first, let's employ the tabular approach. I've got a table to fill out. As we evaluate the function, f of x equals x over the square root of x plus 1 minus 1 at several points near 0, and use it to estimate the results of the limit. As you can see, I'm getting closer and closer to 0 from the left and from the right. The table kind of works its way in to 0 from the left and the right. So I've got that graph plopped into Desmos. We're going to type in these numbers. I've got the function f of x defined with a table to type in. I've got it set up so that when I type in x1, it's going to evaluate the x1 into our function. So negative 0.1, but 1.94. Negative 0.01, 1.99. Negative 0.001, well, 1.999. Now at 0, the function's undefined. If I plugged in 0, I would have 0 divided by the square root of 0 plus 1 minus 1, which is 0 divided by 1 minus 1, 0 divided by 0, undefined. But as we can see, as I get closer and closer to 0 from the left, the function tends to be equal to 2. I get closer and closer to 2 from the left. Let's see if that happens from the right. So now we had 1, 2.41, 0.01, 2.004, and 0.001, 2.004. So as you can see from the table, I'm kind of sandwiching it in from the left and the right. As I get closer and closer and closer to 0, the function tends to be equal to 2. This does not necessarily mean that at 0, the function is equal to 2. As you can see in the middle, the value of the function at x equals 0 is undefined. So using that table, the limit as x approaches 0 of f of x equals 2. I don't know what the function's equal to at 0, but I got closer and closer and closer to 2 from the left and from the right using that table from Desmos here. Okay, now we have a different limit to discuss. Discuss the limit, identify the limit as x approaches 0 of the absolute value of x divided by x. Let's go ahead and do the same thing. We'll put this into Desmos. What is the limit of the absolute value of x divided by x as x approaches 0? Well, as you can see, as x approaches 0 from the left, my function's always equal to negative 1, because I'm dividing the absolute value of a negative number by a negative number. So I'm taking the absolute value of a negative number, which turns it to positive, and then dividing by that same negative number. So I'm always going to get negative 1 out. When I approach 0 from the right, it's just the opposite. It's positive 1. The absolute value of a positive number is positive, divided by that same positive number would still be 1. I approach negative 1 from the left. I approach positive 1 from the right. How can I have a two-sided limit exist if I don't have the same behavior from either the left or the right direction? So this limit actually does not exist. The limit does not exist. And when we say the limit does not exist, we must give the reason why. The limit approaches two different numbers. It approaches negative 1 from the left and positive 1 from the right. So therefore, our limit does not exist. It's a good example of looking at a picture to reason through a limit investigation. We also did an example just a minute ago on using a table. A couple good ways to find a limit, making a table or looking at a picture. Okay, let's look at another table here. Discuss the limit of 1 divided by x squared as x approaches 0. Insert a table. I'm going to change this to f of x1 so that Desmos will auto-fill it in for me. Looking at the picture, I have a pretty good idea of what's going to happen as I get closer and closer to 0. Looking at the graph, as x gets closer and closer to 0, the function is going to increase without bound. Every time I get closer and closer to 0, the function is going to go higher and higher and higher. And that's going to the same thing happen on the right side as well. So I type in 0.1, 0.01, 0.001. That's 100, 10,000, and a million. Every time I pick a number that's closer to 0, I'm going to go ever higher and higher and higher. That's an example of unbounded behavior. At 0, the function's undefined because 1 divided by 0 squared cannot be evaluated because we're dividing by 0, undefined. I could do the same thing with the negatives. Negative 0.1, negative 0.01, negative 0.001. The function does not approach the same number because it doesn't really level off. It doesn't approach the same number because it grows ever higher and higher as x gets closer and closer to 0. That's an example of unbounded behavior, and the reason why we have a vertical asymptote at x equals 0. 100. And 1,000. And a million. Let's put mil. And based off of that table, we can see that the function has unbounded behavior. Every time I get closer and closer to 0, the function gets ever higher and higher. So the limit fails to exist. The function has unbounded behavior as x gets closer and closer to 0. Once again, if you say that a limit fails to exist, please give the reason why. We had approaches two different numbers from the left and the right. We had unbounded behavior. The last case that a limit would fail to exist would be oscillating. I believe that's in this next example. Discuss the limit as x approaches 0 of the sine of 1 over x. Look at these values that the table has us type in. We're taking the constant 2 divided by an increasing multiple of pi. Pi, 3 pi, 5 pi, 7 pi, 9 pi, and 11 pi. So I'm getting closer to 0 from the right because I'm taking the same value. I'm dividing by a larger number. What's going to happen to our function when I do that? So type that into Desmos, the sine of 1 over x. Make sure we are in radians here. Yep. Okay, we're in radians. All right, f of x1. So we had 2 divided by pi, positive 1. 2 divided by 3 pi. 2 divided by 5 pi. As you can see, as I get closer and closer to 0, starting at 1, then I come down. As I get closer and closer to 0 from the right, I approach negative 1. Then I turn the corner. As I get closer and closer to 0 some more, I start going up towards positive 1. Then I get closer and closer to 0 some more, and I start going down to negative 1. It's the same process again and again and again. This is an example of oscillating behavior. I'm either approaching 1 at some points in time, or I'm approaching negative 1 at other points in time. If I do 2 divided by 7 pi, it's the same thing. I can make these negative. The same thing, negative 2 divided by pi. Negative 2 divided by 5 pi. Negative 2 divided by 3 pi. Out of order here. Let's go 3 pi. And 5 pi. So from the left and the right, the function has what's called oscillating behavior. It oscillates between different values of 1 and negative 1. 2 over pi, we had positive 1. At 2 over 3 pi, we had negative 1. And it just kept bouncing back and forth. As I got closer and closer to 0, sometimes I was either approaching 1 or negative 1. So that's not the same number from the left and the right, and therefore the limit does not exist. So the limit does not exist because the function oscillates between either 1 or negative 1. Of all the reasons that a limit might fail to exist, this one is probably the most rare. Unbounded and approaching different numbers from the left and right happen quite a bit more than oscillating behavior. It's usually these special examples of trig functions like the sine of 1 over x or the cosine of 1 over x, and so on. All right, so I think we're going to call that here. We'll stop the video for a minute, and I will come back and finish up the slides for part 2 of Standard 3.